Transformers have its roots back to 1831, where Michael Faraday could conclusively demonstrate that there was a relationship between voltage and magnetic flux. He conducted experiments within coils of wire and created the first transformer. In this project, we have identified the distance between the primary and secondary coils as a factor which will affect the efficiency of power transfer. The basic concept behind a transformer is electromagnetic induction, founded upon Faraday's law of induction and Lenz's law. Due to the ratio of the number of coils between the coils, the voltage can either be stepped up or down, without the two circuits being in contact. With this concept, we thought about wireless electricity.
Now, I'm going to show you the setup of our experiment. The plug is connected to the mains. The plug's live and neutral wire are connected to the lamp. The lamp is connected by two other wires that are connected to the primary coil. The lamp is to change the frequency from 60 Hz to 30 to 40,000 Hz. The alternating current flows through the empty solenoid, which is the primary coil. The alternating current produces an oscillating magnetic field, which is absorbed by the secondary coil. The magnetic field is then converted to electric current by the secondary coil to use to power the bulb. Now I'm going to show you how the experiment works. As the current flows from the mains to the primary coil, it produces a magnetic field which is absorbed by the secondary coil. As I push the secondary coil closer, there is sufficient energy to power up the bulb. As I push even closer, the frequency of flickering is high as it is the optimum distance between both coils. As I push closer, the bulb stops flickering as it is due to back electromotive force.
Here are the results we received. We did the experiment twice to reduce random error. Both the average transmission power were both in the range of 2.4 watts to 3.1 watts. The power reception peaked at about 1.95 watts. The maximum power efficiency was approximately 74%. From the table, when the distance between the two coils increases, the efficiency of power transfer decreases. This due to the fact that the further the distance from the source of energy released, the greater the area of which the energy will be dissipated. Therefore, the amount of energy tapped is lower. There are two interesting findings. Firstly, the current increase initially, then decrease between the two coils gets further. We believe that the 60 watts lamp was connected to the transmitting circuit in a parallel manner as the resistance increased. Secondly, the average transmission power with the distance between the two coils of 1.0 cm is less than 2.0 cm. We believe 2.0 cm is the optimum distance between two coils. Another reason we conclude is that the circuit experienced an increase in resistance due to a counter electromotive force when the distance between the coil was 1.0 cm.
We have some possible errors and also precautions to take note of. Firstly, we have an unstable initial value. The value on the multimeter shot up initially and then comes to a stable value. This is due to the surge in of large magnetic flux initially when the switch is turned on. Another possible error could be due to the direction of the face of the coil, which affect the direction of the magnetic field. Hence, it is important for us to note that the two coils must face each other at all times. Another possible error could be due to the resistance of the circuit, which will increase as the electrical component gets heated up. This will cause the current to be lower. So we must allow the circuit to cool down before continuing with the second reading. Lastly, we have the precaution to take note of is that the circuit is connected to the mains. Hence, it is important for us to be careful while handling with those wires. In conclusion, the distance between the two coils does affect the efficiency of power transfer. Our science textbook states that an alternating current produces a changing magnetic field in coils. By Lenz's law, an induced electromotive force will give rise to a current in the nearby coil, where magnetic field will oppose the original change in magnetic flux. Our project has verified this claim experimentally. The efficiency of power transfer is very low initially, but after some research and modification, we managed to increase the power transfer to approximately 74%. From our results, we can conclude that wireless electricity is possible. However, further investigation is to be carried out to determine its feasibility.